Check, check.
Thank you very much. Good morning, children. Lovely to see you. Okay, guys, please get your name tags out, all the usual stuff. Your laptops must be shut if you may. Morning, Winston. All right, okay. Make sure to time the polls. Make sure to time the polls. 90 seconds. Make it 60. 60 seconds. All right, let's begin. So we are continuing on our series of lectures on training the network. How many people do we have on Zoom? Okay, not bad. That means that about 200 people are missing from the class. We will take attendance, right? So the attendance poll is 426. And here's what we have seen so far. That neural networks are universal approximators. They can model any odd thing, provided they have the right architecture. We must train them to approximate any function, meaning you specify the architecture and learn their weights. The networks are trained to minimize the loss on a training set. Now, does this guarantee that it learns the correct function? Minimizing the loss on the training set. What do we actually want to minimize? Is that what we want to minimize? Can you repeat that, please? The area between? The approximation and the new. So you want to minimize the overall error between the expected divergence between the actual function that you want to model and the output of the network itself over the entire space, whereas what we are really doing is minimizing this error over a small number of training points. And we do this, so this is empirical risk minimization, and we use variance of gradient descent to perform this minimization. And the gradients are computed using, what are they computed using? Back propagation, right? So here was the overall setup. We were given a bunch of training points. We defined a loss over all of these training points, which is the average divergence over the training set. And you initialized all your network parameters. And subsequently, you iteratively computed the divergence of this loss with respect to all the network parameters and the gradient of this divergence with respect to network parameters. And then you took a step. All the network parameters are updated by taking a step against the gradient. And for this, we needed to perform this, we needed to be able to compute this derivative term, the derivative of the divergence with respect to network parameters. And this was computed using backprop. So now here's the other recap. We looked at vector update rules, finally. And just, it's worth spending a second or two on this. As you go through the network, at every layer in the network, the previous network layer output yk minus 1, which represents the vector of outputs of the previous layer, was used to compute the affine vector at the kth layer. And what was the formula for this? Anybody remember? What was the formula for zk as a function of yk minus 1? Miguel? So we had zk equals the weight vector times yk minus 1. Is that it?
In the bias and the weight.
Plus the bias, right? If you have the bias as a separate vector. So this was the update rule where you computed the weight matrix multiplied the y vector to give you the new affine vector z, and then what happened in the next step? From this we computed the output of the yth layer, and what did we do for this? The activation function, right? So yk equals, just using these two rules at each layer, you could just keep stepping forward. And now if I were to draw the influence, the dependence, each yk minus 1 influenced the corresponding zk, which influenced the corresponding yk, and this happened. And then eventually, the final output of the network was compared to the desired output. And so this, every yk eventually influences the divergence, right? So if I were to write down the derivatives on this picture, this guy over here is going to be whatever the divergence that you might have computed, or whatever the derivative that you might have computed of the divergence with respect to yk. And then what was the derivative that you had out here on the edge which linked zk to yk? What was that? Guys, yes. How did we represent that? You know what? Come on, help me, fellas. So Miguel, you know the answer to everything.
The derivative of dyk.
So this would have been
Reverse that, sorry. dl dyk abc.
And if yk and zk are vectors, what is that?
A matrix.
This is going to be the Jacobian, right? Does everybody remember this? Right. And what was the derivative here?
The weight.
The weight matrix. And so this was very simple, right? And then when we were, everybody remember this? I hope you do. And then when we computed our derivatives going backwards, you would compute your derivative until here. So that would be just, the derivative of the divergence with respect to yk. And then what was the derivative of the divergence going back to zk? Anybody remember? What was that? The product. And so the derivative of the divergence with respect to zk was the product of what and what? Can you say it aloud, please?
With respect to yk,
Derivative of the divergence with respect to yk times what?
times the divergence of yk with respect to
The derivative of yk with respect to zk. And so this, all we did was multiply the current derivative with the derivative for that particular link, which was the Jacobian. And then if I wanted to take a step back and compute the derivative with respect to yk minus 1, what did I need to do? Anyone remember this? What was this? Help me, guys. So Evgeny, what was it?
median matrix.
Pardon me, can you say that aloud, please?
The summation of previous term multiplied by the LDK.
The summation?
Product.
The product. So this was going to be the derivative of the divergence with respect to zk multiplied by the what was that term? Wk. And so this, you just could iterate, you could just step back through the network. Whatever derivative you had over here, you multiplied it by the Jacobian to get the divergence here. Whatever derivative you had over here, you multiplied it by the weight matrix to get the derivative at yk minus 1. You could keep stepping backwards, right? And then you had two more things to compute. And the two things to compute were the derivative of the divergence with respect to any bias vector bk. And what was that? So over here, if you just look at this, I have this relationship. So what was the derivative of the divergence with respect to the bias, bk? What was it? What was the derivative of the divergence with respect to bk? Yes?
The derivative of the divergence with respect to ZT.
This was just the derivative of the divergence with respect to zk. Do you remember that? Does everybody remember that? Can you raise your hands even if you don't? You can lie to me, please raise your hands if you remember it, all of you, right? And those of you who haven't raised your hand, please raise your hand so you go ahead. And you haven't remembered it, have you? So never mind, still lie to me, please, okay. And what was the derivative of the divergence with respect to WK over here? We saw this rule too, right? And we saw that the derivative of the divergence with respect to WK was YK minus 1 times the derivative with respect to ZK, right? So this was at any edge, if I have an edge of this kind, Z going to Y, and then this goes on to the divergence with the W here, then the derivative of the divergence with respect to W was going to be, Y going to Z was simply Y times the derivative of the divergence with respect to Z. So the variable at the beginning of the edge times the derivative for the variable at the end of the edge. So that was the simple rule that we had. Is there a faint recall that this was mentioned towards the end of the last class? I'll make a post about this on Piazza. Please take a look. This is in your homework. You should have known this by now, right? And so we just had the entire pseudocode for back propagation, where you just compute a first forward pass, and then in the backward pass at each step, as you compute the derivatives backward, you keep right multiplying by the Jacobian and by the weight matrix. And in order to compute the actual derivatives with respect to network parameters, the derivative with respect to BK was just this. The derivative with respect to WK was, the Y at the previous layer times the derivative with respect to the ZK. So it was on the slide, but you guys didn't read them out. Okay, here's a poll. A minute up. Okay, guys, time's up. Anybody want to answer this? Is the first statement correct?
Yes.
Second? No. Third? No. Fourth? No. Okay, right. And so again, just to go back.
Okay, so.
Can you turn your mic off, please, if you're not answering the class? So here, once again, we were just using the chain rule. If I write it in scalar form, we just read simply the derivative of the divergence with respect to yk times dyk over dzk. This was just the scalar chain rule. And what we saw over here was the vector form of it, where instead we had the derivative of the divergence with respect to y times the derivative of y with respect to z. It's exactly the same as the scalar chain rule. Nothing changed, except now that these things are vectors and matrices. And this is the rule that we keep following all the way back. Okay. So let's move on. Yeah, was there a question? No. So we've sort of looked at backpropagation rules to compute derivatives. And we know that backpropagation computes derivatives for gradients, which are employed within the gradient descent rule, right? So the question is, does this actually work? Does gradient descent converge and give us the correct answer? What are the rates and how does it converge? We're going to look at rates, restrictions, Hessians. And in the next class, we're going to look at ways of speeding this up. So here's the first question, is backprop always right? So for the longest time, the term backprop was actually used to refer to the gradient descent algorithm itself. Do you mind shutting your laptop there? Yeah, which we use to update the parameters. Although backprop is only used to compute the gradients, which is used inside the gradient descent rule. So this is just a minor abuse of terminology. So the actual question is, does gradient descent find the correct solution when it finds the actual minimum of your loss function? And for this, again, remember this, what we really wanted to do was to minimize the error count as we saw in the upper picture. But what we did was to compute a proxy for this error by changing the activation function to something differentiable and changing the manner in which we computed the derivatives to also be something, the error to also be something differentiable. And this has some consequences. So let's go back and look at the problem of classification. In classification problems, the classification error is a non-differentiable function of the weights. And so the divergence function that we minimize is only a proxy for the classification error. And minimizing the divergence may not minimize the classification error. How so? Consider the simple example. Let's say I'm performing a binary classification task, and I have a collection of data from both classes. So the red classes and the blue classes. By the way, you there, do you mind turning your phone upside down, please? Turn it, do you mind flipping it face down? Thank you. Right, so let's say I have a collection of, no, the person behind you, right? And please shut your laptop there. Thank you. Rules of the class, okay? Let's say I have a collection of red dots, red instances and blue instances, a very large number. And they're nicely linearly separable. So if I were to use just a threshold activation with the perceptron rule, would it find a decision boundary? Yes. Now, if I were to perform gradient descent to compute, minimize the total loss, would it find a decision boundary? Yes. Also yes, right? Now, and the two are likely to be the same. They're not going to be very different in this situation. But then now I add one little new training instance, this red dot. The two classes are still linearly separable. Will the perceptron rule find a linear decision boundary? Yes. It's going to give you something like this dotted line, right? What about gradient descent? What will it give you? Will it find this line? No. So let's assume that I have 1 million of those red dots and blue dots, and I just add this one little red dot. How much will it affect the overall loss? Small. Trivial. So will gradient descent swing around to a completely different solution? It will not, right? Gradient descent is probably going to perturb the solution just a little bit, and that's it. So although the solution exists and is within the class of functions that is modelable by the network, gradient descent will not find it. So, or let's say I perturbed, instead of this red dot here, I moved it here. Once again, the perceptron learning rule is going to find the decision boundary. Gradient descent is just going to move things a little bit, and it's going to make an error on that one instance. And, or if I put my spoiler, this extra dot, which I'm calling the spoiler out here, the perceptron rule, again, the classes remain linearly separable. So the perceptron rule is going to find the separator, but gradient descent is not. Again, the solution lies within the class of functions that can be modeled by the network. It's just that gradient descent won't find it. So as I keep moving that dot around, the perceptron rule chases the solution because a solution always exists and finds it, but there's no guarantee that the gradient descent technique, which uses the proxy loss function, is actually going to find the solution. So is this a good thing or a bad thing? What do you think? Are you sure? Yeah.
It's a good thing because
What?
that could be overfitting.
So it's actually a good thing. Why is that so? The perceptron may change greatly upon adding just a single new training instance. I could have a billion of those red dots and blue dots nicely separated, and then I just add one little instance out here, and the perceptron rule is going to swing around and give you a completely wildly different solution, whereas gradient descent is going to not change very much. So the perceptron rule has low bias, meaning if there is an answer, it will find it. But it has high variance, meaning I can move just one training point, and the solution is going to change wildly. So I can make the solution swing crazily by just moving one little training point around. So it has very high variance. It swings around, it is very sensitive, but it has low bias in that it's always going to find the correct answer if it exists. Whereas the gradient descent approach is not zero bias. I can move one point around and it's not going to move very much, and it will make mistakes very often. But it's not going to be sensitive to outliers and noise. And so backprop or gradient descent prefers consistency over perfection. It is low variance, and this is something that we actually like. Now, this is for a simple linear classifier. Even if I have a nonlinear classification problem of this kind, the perceptron, the new multi-layer perceptron would find a decision boundary like this red one here. Adding one extra dot in the wrong place is not going to change the entire solution. It's only going to change it just a little bit. And so backprop, or rather gradient descent using gradients computed using backprop, will often not find a separating solution, even though the solution is within the class of functions learnable by the network. This is because the separating solution is not a feasible solution of the loss function. And the resulting benefit is that backprop trained neural network classifiers have lower variance than an optimal classifier for the training data. The optimal classifier for the training data may be able to separate the classes, but then it's going to be very sensitive to the specific set of training points you have, whereas backprop is going to not be so sensitive. Any questions? Questions? Okay. Cool. Yes.
Why do we prefer lower variance over lower bias? Or
Tell me this. Is this behavior something acceptable to you?
well, it depends on how well you clean your data.
So no, but this is the data I'm giving you. Is it acceptable?
No, but like
Why? Because this is, that one dot could just be an outlier in your training data. You're going to be chasing outliers all the time. So our preference is to have consistent solutions which don't change it tremendously. We'll see more of this in a few classes from now, maybe in the next lecture or the one after that. Okay. So can somebody answer this question for me? True or false? Okay, thank you. Right? Minimizing the differentiable loss function will not minimize classification error. Here's the other problem. In all of this, I'm assuming that the loss function has one nice clean minimum. The loss surface can be hideous, like this one over here. Lots of valleys, lots of little local minima. Which one are you going to find? All gradient descent does is to walk down. It's going to walk down into the closest local minimum. And what does the loss surface actually look like? There are many, many papers on this subject. And almost all of them indicate that the loss surface has far more saddle points than local minima. A saddle point is one where it's a minimum in one direction, but not a minimum in the other direction, like the picture over here, like a saddle. A saddle is a minimum in this direction, but not a maximum in the other direction, right? So the slope is 0, and the surface increases in some directions and decreases in other directions. Now, gradient descent is going to, if you started off out here, gradient descent is going to find its way to this point where the derivative is 0, and it's just going to get stuck there. Also, when you have lots and lots of local minimum, then for very large networks, the theory seems to indicate that all of these local minima are roughly equivalent, and they're not very different from the global minimum. This doesn't hold for small networks. So in this case, arriving at a local minimum is not a terrible thing to be doing. But again, the question is, do we really want to do this? So what we've seen so far is that neural nets can be trained via gradient descent, where backprop is used to derive the derivatives. Backprop is not guaranteed to find a true solution, even if it exists and lies within the capacity of the network to model, because the optimum for the loss function may not be at the true solution. The true solution is being their ideal classifier, right? And for large networks, the loss function may have a very large number of unpleasant saddle points or local minima, which backprop might just end up stuck in. So let's take a look at what kinds of things can happen. So far we've assumed that training arrives at a local minimum. Does it even arrive at a local minimum? Let's ask that question first. Does it converge? And if it converges, how long will it take? Now, MLPs are really hard functions to analyze. They're complicated nonlinear functions. So we use this well-known streetlight effect. We're all familiar with the joke where some guy loses his keys in a dark club and is found searching for them under a streetlight. And when the policeman asks why, he says, well, at least I can see things here. So this is basically what we're going to do. We don't know how to analyze complicated neural networks. We know how to analyze convex functions. So we're going to analyze convex functions, and we're going to sort of pretend that whatever we've learned over here applies to the more complex case. Now, what is a convex function? Does anybody know? What's a convex function? Yes?
A function where the line segment between any 2 points lies completely above the function itself.
Thank you. So a convex function is a function of this kind where if I just draw the function, and if I take any 2 points on the function and draw a straight line between the two, every point on the straight line is going to be above the function. It doesn't matter which 2 points I take. For example, if I took this one and drew a line, the line is entirely above the function. So this function is convex. Now, if I have a function of this kind, is this convex?
Oh, so far.
Mm-hmm.
So far, yes.
Pardon me?
So far, it looks like.
Is it convex, guys? If I took this point and drew a line, is it above the function? So is it convex? No. So you get an idea of what a convex function is. There's a corresponding notion of a convex set. A convex set, just applying the same concept, what would a convex set be? Anyone?
Set of points where the one on the slide.
So if I have a set, and the set is such that if I take any 2 points inside the set and draw them up, connect them up with a line, every point on the line lies within the set. Is a convex set. So the sets to the top are convex. The set at the bottom is not convex, because if I can take 2 points and connect them up, and the line goes outside the set. So we're going to deal with convex functions. Now, this is also the notion of convergence. Now, if I have a function and I'm performing gradient descent, the principle that I sort of hoodwinked you with was that if I keep stepping against the derivative, eventually I'm going to get at the minimum. Will that happen? So let's say I have a function of this kind. If I keep walking against the derivative, if I keep taking small steps, the hope is that eventually you arrive at this point, kind of, in a systematic manner. But what you could do is to make, worse things can happen. Your initial step could be too large, so you overshoot. Then you would have to come back. And so you can also arrive at the solution by oscillating back and forth. And if the initial step is way too large, you can just completely so you can have different kinds of behavior. you can just converge cleanly to the solution, or you can come close to the solution and keep bouncing around, that's jittering, or you can even diverge, you can just completely go away from the solution. So what are the conditions under which these things can happen? For this, I'm going to look at quadratic functions. What is a quadratic function, anybody? What is a quadratic function?
With the term with the power greater than 2.
Greater than 2, is that a quadratic function? A quadratic function is a function that has the form y equals, I have this term half here for convenience, ax squared plus bx plus c. So what will the shape of this function be?
Parabola.
It's going to be a bowl, it's going to be paraboloid, right? It can be a bowl down, or it can be a bowl. It can be a bowl going upwards or a bowl going downwards. When will it be a bowl going upwards with a minimum? A is positive. So if A is positive, then for positive A, this is going to look like so, with a bowl going upwards, correct? So does it have a unique minimum?
Yes.
It's quadratic. You all know how to solve for the minimum of a quadratic function. Minus b plus or minus square root of b squared minus 4ac, right? Or 2a. Now, so that's neat. But suppose, okay, let's take another topic. How many of you are familiar with Taylor series? What is a Taylor series?
Method of approximation.
Exact approximation function based on its derivative order.
So the Taylor series approximation of a Taylor series is a series approximation of a function where you can pick any point. If I have a function f, the function may have some shape, right? I can pick some x0, and I can write f of x as approximated by f of x0 plus x minus x0 times f prime of x0 plus half of f double prime of x0 times x minus x0 squared plus 1 over 6 third derivative. It's a series approximation. Everybody remember this? You must have encountered this in school, right? So this is, and when will it be exact? What is the specialty of this Taylor series? So the specialty of the Taylor series is this. If I just take the first term and I truncate it after the first term, the Taylor series approximation and the value of the function are both correct at x0. If I truncate it after the second term, meaning just make it a line, right? That's going to be this approximation. The slope of your approximation and the value of the function itself, both of them are going to be accurate at x0. If I truncate it after two terms, what is the corresponding generalized extension? It will be a parabola, but the slope, the value of the function, the slope, and the second derivative of the function will both be the same as that of the original function at this location, right? Everybody get that? Okay, so now, if I took a quadratic function of this kind and took a Taylor series approximation around any x0, how many terms would the Taylor series approximation have? 3. Why 3?
To approximate a parabola.
Why 3? Why only 3? Yeah.
Well, the derivatives will be 0.
The third derivative of a quadratic function, what is the third derivative of a quadratic function?
0.
0. So they're only going to be the first two terms. And in this case, is this guy over here. It doesn't matter what x0 is. This is going to be the Taylor series approximation. Is this an approximation? At this point, will this be an approximation?
No.
It's going to be exact, right? Because this is a quadratic function. The two sides are guaranteed to be the same. And so I can take this function over here. I can start off at any x0. If I write Taylor series approximation for it, it's going to look like so. Is everybody with me? That makes sense? You guys at the back. Make sense? Okay. So now can I minimize the term to the right? How would I minimize it? Help me. Rishikesh, how would I minimize this? Differentiate it? Okay, can you help me differentiate it? If I differentiate it, what's it going to be what's it going to look like? df over dfx. What is this? Continue.
F double prime of x0.
So this is going to be f. The derivative of this term is 0. It's right. It doesn't matter, right? The derivative of this term is going to be just f prime of x0, correct? Yes? And what about the second term?
F double prime of x0
Plus f double prime of x0 times x minus x0. That is the derivative of f, correct? Does everybody with me? Right. And if I equate it to 0, I should get the location of the minimum, assuming it's a ball. Yes or no?
Yes.
Okay, so what will this give me? I can write this as x minus x0 equals minus of f of x0 divided by f prime of x0 divided by f double prime of x0. Correct? Which gives me, of course, this very simple solution, which is x equals x0 minus f prime of x0 divided by f double prime of x0. This is the x at which the function is minimum. Right? Yes or no?
No,
Who says no? Yeah.
it's one step back from x0 to the place that the minimum.
Are you sure? I've just computed the derivative and I've equated the derivative to 0. Where is the derivative 0 for a quadratic?
Minus a over a,
Yeah, where is the derivative 0?
the minimum.
The minimum. So what is that x hat? When I equate the derivative to 0, that is the minimum, correct? Yes or no? I've literally just solved for the minimum. Okay, so we spend a lot of time on it. We know how to, so here's the equation of a quadratic, and here is, I can solve for the minimum of a quadratic trivially enough, but I can also try to walk down the quadratic using gradient descent. Start at some initial value and then keep taking steps in this manner, right? So if I were pass using gradient descent, the iterative update is going to be wk plus 1 equals wk minus eta times the derivative with respect to x at wk. Everybody with me? Is there a step size? I mean, how fast does it converge? If step size is eta is small, will it take a lot of steps?
Yeah.
Okay, is there a step size where it will converge in one step? Mm-hmm. Yes, what is that step size? Is there an answer on the board for this? Is there an answer on the board for this?
Yes.
What is the answer?
F prime x naught over f double prime.
So this is simply, I can write this as x hat equals x0 minus eta times f prime of x0, correct? That's what this is. And if eta equals 1 over the second derivative, you're going to get there in one single step. That makes sense to everybody? Okay? So just writing this thing out as a derivative, if I write the quadratic as half aw squared, the second derivative is a. And so just a step size which equals a inverse. Inverse will get you to the optimum in a single step. Everybody with me? Okay. So just using this, suppose I have a quadratic. I'm spending way too much time on this, but let's see if I can hurry up. Suppose I have a quadratic of this kind. I start off at some point, x0, right? And then I just use the update rule, which is xk plus 1 equals xk minus eta times f prime of xk. This is your standard gradient descent rule, right? If eta equals 1 over f double prime of xk, how many steps will I take to get to the minimum?
One.
Just one. Okay. So directly out here. If eta is less than 1 over f double prime of xk, what happens? Will I get to the solution in one step? So then what must I do? Take additional steps, right? So this is my optimal step size, guaranteeing solution in one step. If I do this, I'm going to be doing this. Correct? What if eta is greater than 1 over f double prime? What will happen? Then I'm going to go here. And then I'm going to, now the derivative will point the other way, right? And so I'm going to be doing this. Is there a step size which is bad?
Like a really big one.
How big? Yeah.
Maybe like 2 times what?
If I take a step size which is 2 times 1 over f double prime, where will I end up? Exactly on the other side. And then I take a step back, and I'm going to keep bouncing back and forth. And if it's greater than 2 times, I'm going to go up, right? And so this is basically what will happen. The optimal step size is 1 over the second derivative of the quadratic. And if you have exactly the optimal step size, you're going to get to the solution in one step. If it's smaller, you're going to take many steps. And the smaller the step size is, the more time you're going to take to converge. If it's larger, you're going to overstep, but maybe you will oscillate back. But if it gets larger and larger, the amount of time you're going to take to get to the optimum is going to keep increasing. And then when it's twice the optimal step size, you're never going to get to the minimum anymore. If it's greater than that, you're going to walk straight out of the minimum. So guys on Zoom, can you actually please mute yourself? Thank you, right? Okay. This makes sense to everybody? Okay. Now this is for a scalar function, right? Now, if the function is not quadratic, let's generalize. If the function is not quadratic, I can still use the same principles. And what I can do is I can take a quadratic approximation at each point. And if my step size equals the inverse of the second derivative at each point, I'm at least locally going to get to the optimum. If it's more than twice that, I'm going to just, the iterations are just going to blow up. Okay? Everybody with me so far? Okay. Now this is for, we can get divergence if eta is greater than 2 times eta opt. That's for a scalar function. But what if you have a multivariate function? So suppose I have a function of 2 variables. And let's assume the thing is still quadratic. So what would a function of 2 variables look like? Let me plot this. A function of 2 variables might be f of x1, x2 equals half a11 x1 squared plus b1 x1 plus half a22 this is x1 squared, yeah, x2 squared plus b2x2 plus c. So it's going to be a sum of two quadratics, and then this is assuming that the coordinates are axis aligned. This is the simplest case, but it's good to analyze this, right? So now it's a sum of two quadratics. If I were to plot it, it's going to look something like this, where it can also be at an angle, in which case, you're going to have a non-diagonal Hessian, but we don't, and how that maps onto this is on the slides. It's good to just analyze this axis aligned case. Look at what happens. If I draw the level sets, the equal value contours, they're all going to be ellipses. Because if I fix x2, then this guy is going to be some value, which is just a function of x2. For different values of x2, this is going to change, which is just a constant as far as x1 is concerned. But this portion of the curve is not going to change. So for different values of x2, if I take a slice at different x2s, each of the slices is going to look like a bowl. The heights of the bowls are going to be different, right? So also if I fix x1, then it's just going to be a function of x2. So for different values of x1, if I took slices at different x1s, each of those is going to be a bowl. The heights are going to be different. The minima are always going to be at the same point. The minima are always going to be right in the center of that ellipse, right? Okay, so now let's just consider this case. So let's say I have a function of two x2s, right? Two variables. Now, over here, what is the optimal, if I'm performing gradient descent, what is the optimal step size for x1? 1 over a11. What is the optimal step size for x2? 1 over a22, right? So now let me say that this is my function. And let's say I start at this point, okay? If I take an optimal step size for x1, then what will happen to the solution? Along x1, it's going to arrive here in a single step, right? Does that mean that along x2, it's going to arrive here in a single step also? Right? What could happen? Anything can happen. Why? Each of the two will have a different optimal step size. And in our gradient descent rule, we have the same step size for every component, correct? So just gradient descent basically is always going to take a step perpendicular to the equal value contour, because we know the gradient is orthogonal to the equal value contour. And so we always take the same step size for every single component. We know this from the gradient descent rule. And so that's going to lead to this problem. The optimal step size can be different for different directions. And an optimal step size in one direction can cause all kinds of behavior in the other direction. So let me just try to draw this with pictures again, right? First, if A11 is large, what does it tell me? Is the bowl steep or shallow? Steep along x1, right? Because a small change in x is going to cause a large change in y. And so should the step size be small or large if A11 is large? Because the function is very steep, and vice versa, right? So let's draw this picture. And say I have a figure of this kind, and let's say A11 is 2 and A22 is 0.5, okay? What is the optimal step size along x1?
1.
This is 0.5, right? What is the optimal step size according to this guy? 2. Okay. So now this is x1, and this is x2. So let's say I take a step size which is, say, 0.25. What will happen? I start from here. If I take a step size which is 0.25, what will happen? It's going to be lesser than the optima for both of these guys, right? So what would happen? It's going to keep converging to this, right? Suppose my step size is exactly 0.5. What happens? It's going to, for x1, it's going to go here in one step. But for x2, you're going to take a small step. So the very first iteration is going to take you here. And then it's going to go down slowly in this direction, right? If the step size is, say, 1, what will happen? It's going to go here, and it's going to do something like this, correct? Because it's still less than, or will it? If the step size is 1, what will happen? It's going to go here, and then along the x direction, it's going to keep oscillating. So actually, it's going to go and do something like this. It will eventually get to the optimum along the y direction, but along the x direction, because the step size is twice 0.5, it's never going to converge. That makes sense to everybody? Right, so here's the behavior that you would see. You can end up with all kinds of patterns. You want the things to converge as fast as possible, meaning you want the step size to be close to the optimal step size for every component, right? On the other hand, the optimal step size for one component can cause divergence in the optimal along the other component. Did that make sense to everybody? So what is the condition that you would need to impose for guaranteed convergence?
Lesser than both.
Lesser than both. The step size must be smaller than the 2 times the optimal step size for. Actually, if you want the fastest convergence, you want this to be, you want the slope in every direction to be the same, the curvature in every direction to be the same, but at the least, you want the slope to be, the step size to be smaller than 2 times the smallest optimal step size, right? So you want this to be less than the optimal twice the optimal step size for the steepest direction. What can the consequence for this be? I can find the step sizes for all the directions and make it smaller than the optimal step size for the steepest direction. What will happen to the other directions?
Overall learning would be very slow.
Because you're going to get, because things become very, very slow, where if I have a function of this kind, where it's very steep in this direction and very shallow in this direction, making sure that I converge in this direction results in essentially no movement at all along the y direction. So you have this behavior where you want the step size to be less than twice the smallest optimal step size, and this makes the learning very, very slow, right? And if it's now this also holds for non-quadratic functions. For any non-quadratic function, we can do the same thing. I can come up with a quadratic approximation using Taylor series, even when the function is multivariate. The Taylor series approximation for non-quadratic functions is going to have a Hessian as the second derivative. But otherwise, the whole thing still works, right? And then once again, you're going to find that you have, if you look at the Hessian of the function, the eigenvalues of the Hessian of the function give you the curvature along different directions. And you want the step size to be smaller than twice the smallest optimal step size in any direction. So here's what happens. Convergence behaviors become increasingly predictable as the number of dimensions increase, because as the number of dimensions increase, you really have no idea of what the different curvatures are. And for the fastest convergence, ideally the learning rate must be close to both. Ideally, the curvature will be very similar in all directions. And so for the fastest learning, to get to the optimum very fast, you want the step size to be optimal, closest to both the largest optimal step size and the smallest optimal step size. This can only happen if the two are very similar, right? So in general, if this guy if the ratio of the largest optimal step size to the smallest optimal step size is very large, that means convergence is probably not going to happen in a hurry, because convergence in one direction ensures very slow convergence in the other direction, or divergence in the other direction. So you want the ratio between the largest and the smallest step sizes to be as close to what value? 1 as possible. In general, that won't happen. This is something like a condition number, must be close to 1 for fast convergence. And there are a whole bunch of slides discussing this. Yes?
If we know we can calculate the optimal step size for each component, why can't we just set
Would that be gradient descent?
that still converge?
But that's not really gradient descent. Gradient descent is really taking the step against the gradient, which says that all the step sizes are different, right? And so you're absolutely correct. If you had different step sizes for different directions, then you can kind of try to take optimal step sizes in each direction. It requires computation of the second derivative along each direction. That's really hard, and because back propagation only computes the first derivative, not the second derivative, right? So there are all kinds of approximations for it. But here's the point, that there's a reason convergence is a challenge in these networks. There are parameters with millions or billions of parameters, and there's the optimal scale. You at the back, do you mind shutting your laptop? You're welcome to work on your laptop, go outside and do it, right? So this is but the convergence in one direction does not guarantee convergence in the other direction. That's a problem. But there's another thing. Much of the analysis we saw was about trying to ensure that we sort of arrive at the minimum, in a uniform manner. Is that even necessary? Now, what really happens in a standard network is your loss function is going to be something like this. So if you start off at that point in the small local minimum, if you ensure convergence, you're going to arrive at a really bad local minimum. So over here, is divergence a bad thing? Right? But is continual divergence a good thing? So what would you want happen?
Get out of the small pot into the bigger one.
You want to get out of the small pot and into the big pot. So the way you would do it is to start off with a large step size, which makes sure that you begin stepping out of all of these little valleys. And then you reduce the step size with iterations. And if you do it just right, eventually you're going to end up in the largest valleys. And the deepest valleys, the assumption is that the deep valleys are really wide. And so if you keep stepping out and keep decreasing your step size, eventually where you will be stuck is going to be in one of the deepest and widest valleys, and getting to the bottom of that is a good thing. So the best thing to do is to have a decaying learning rate. Start with a very large learning rate, greater than 2, and gradually reduce it with greater than 2 in a normalized sense, and then gradually reduce it with iterations. And there are very many ways of doing it. So you might have encountered some of these in your homework, that you decay it linearly with the number of iterations. You can decay it quadratically. You can decay it exponentially. For what you do in your homework, which is stochastic gradient descent, there are other criteria that we will encounter when we begin talking about SGD in the next week. And those must be satisfied. Questions?
Can we analytically show that we're more likely to end up in a lesser global minimum if we use a decaying learning rate, or is it just like a practical thing that people found out?
You can actually show it. It's just the math is a bit complex. I mean, with the appropriate assumptions. And so there was yes.
My question's about warm-up. I mean, I've heard in like transformer context a lot of times, like warm-up play weights of the network. Does that matter at all, like when you sort of initialize?
So again, we don't really know what the optimal step size is. So the entire warm-up is about trying to eventually get into a place where you can start off from and get to the optimum from. But again, you don't really perform training in this manner when you train transformers. You perform mini batches and stochastic gradient descent, and we'll deal with that next week. Yes.
So the best scenario in the 2 dimensions should look like the circle.
Exactly.
And if it's possible, we can maybe like squeeze or normalize.
So this is, to do this, you would have to transform the function using the inverse of the Hessian. That gives you Newton's update rule. But computing the Hessian for a two-dimensional function is easy. For a million-dimensional function is quite impossible. And inverting the Hessian is harder still. Right? So, any other questions? Yes?
I was just thinking about what we were saying about like increasing the size of the network increases like the incidence of saddle points.
Uh-huh.
I'm just trying to imagine like this is the increasing the like this strategy of like starting with a high learning rate and kind of trying to jump around until you find one of these valleys. But it just seems like does that help with the like escaping the saddle points? And I don't know if like thinking about the optimization space when we have like the actual networks is helpful to think about the two-dimensional.
If you're just thinking of plain gradient descent, that's not really going to help you escape the saddle points. I mean, it does to some extent because initially you're likely to get out of saddle points.
Right.
But if you're stuck in the vicinity of a saddle point with a small enough step size, you're eventually going to end up stuck at the saddle point.
Okay.
Right? So this is a challenging problem. We'll see some more of this in the next week. Any other questions? Okay. So gradient descent can miss obvious answers, but we saw this may be a good thing, like in this case, right? And convergence issues abound. The loss surface can have many saddle points, and all the perhaps not so many bad local minima. Gradient descent can stagnate on saddle points, and what is this? And vanilla gradient descent may not converge or may converge too slowly, and the optimal learning rate for one component may be the inappropriate for the other component. So who was it? Was it you who mentioned we should have, suggest that we could have different learning rates for different components? Someone did. Okay, Akhil did. Akhil, no. Dhruv. Somebody there along that line. Okay, whoever did, right? So that makes sense, right? But then again, what do we know about the optimal step size for any component? We are not computing second derivatives. So this is really hard. Computing second derivatives is very, very expensive. It takes the squared as many computations as computing the first derivative. We don't want to do it. Yet we want to keep track. We want to have different step sizes for different components, and we want to keep track of how things work. So a lot of work goes into trying to figure this out. And first. Okay. Someone on Zoom want to answer tell me if the first statement is correct? Is there anybody on Zoom? Lots of people. Go ahead. What about the second statement?
It's false.
And the third one?
False.
Right. So step statement, the sizes that are greater than twice the inverse second derivative can cause gradient descent to diverge. This is not a bad thing. It can help you escape local minima. On the other hand, with the optimal step size, you can actually get there in a single step. So you don't need decaying learning rates. Even with a fixed learning rate, you could get to the optimum. So the story so far, we found divergence convergence causing learning rates may not be a bad thing for ugly loss functions. Decaying learning rates provide a good compromise. But many of these convergence issues arise because we are forcing all components to have the same learning rate, the step size. Can we modify this, right? So if I take a step back, the problems arise because of requiring a fixed step size across all dimensions because we want to perform gradient descent. And gradient descent makes sense in high dimensional functions because that's the easiest thing to be doing. Computing derivatives is easy. But then let's try releasing this requirement that every single component must have the same step size. There were lots and lots of ways of doing it. And the two things that are on the slides are rprop and quickprop. Rprop gets rid of the derivative altogether and just uses a step size. So uses the sign of the derivative. Quickprop tries to estimate the second derivative, except the way it does it is by looking at differences. So if I take 2 steps, then the first step gives me a notion of a distance and a change in loss. The second step gives me a notion of a distance and a change in loss. So from each of the steps, I can get a notion of a derivative, a slope, an approximation to the slope. And from the slopes at 2 consecutive steps, I can get an approximation of the second derivative. And then I can use that to optimize my step size along each component. Quickprop is on the slides. I'll just talk about rprop because it's a really, really easy concept. Here's what we're going to do. It's a resilient propagation algorithm. It's very simple, and you follow this independently for every component. You can find it in PyTorch. At each step, you're going to, each time for each component, you're going to do something very simple. You're going to say, should I be going forward or backward? How would you do that? I can just look at the sign of the derivative, right? If the derivative is positive, what must I do?
Go back.
Take a step back. If the derivative is negative, take a step forward, right? So let's say I check the derivative now, and I find that the correct thing to do is to go forward. So then I can go forward. But then I go back and I check the derivative again, and I say see that the correct thing to do is still to go forward. Am I going in the correct direction? Yes or no? Right? Right. Am I going in the correct direction? So does it make sense for me to increase my step? Because I'm doing the right thing. So the next time I take a larger step, and then I check the derivative again, I'm still going in the correct direction. Then I can take an even larger step because I'm doing the right thing, right? But what will happen if I keep doing this?
You'll overshoot. You'll overshoot.
I will overshoot, right? So very simple. I check the derivative, I take a step. I'm going in the correct direction, I take a larger step. I'm still going in the correct direction, I take an even larger step, and then I overshoot. So if I overshoot, what would you do? Hector, yeah?
Go to a different minimum.
No, but I overshot the minimum, right? What would be the correct thing to do? Go back and take a smaller step, right? Because obviously I've gone past, so I can go back. It's a very simple algorithm, right? So that's what we do. You start off at an initial value, and this is done component-wise. And you take an initial step, delta W, against the derivative. If the derivative asks you to go forward, you go forward. If it asks you to go backward, you go backward. And then, so the orange arrow shows the sign of the direction of the derivative. The red arrow shows the direction in which you would be moving. Then you arrive at a new location. And then you check the derivative, and the sign of the derivative has not changed. If the sign of the derivative has not changed, you're going in the correct direction. So you increase your step size by some factor alpha. Then check the sign of the derivative again. If the sign of the derivative has not changed, you increase your step size once again by a factor alpha. Keep doing this. Eventually, at some point, you're going to overshoot. Now the sign of the derivative has changed. Earlier, the derivative was positive or negative. Now it's become positive. So what would you do? You go back. And then you multiply your previous step size by some factor beta to shorten it. So it's alpha squared beta, and that's the new step. And then from there, if you're going the right direction, you can increase the step size and so on. Yes?
You do this per component?
Per component. So every component now has an independent update. And this really, really works. It's amazing. It works as well as, very often works as well as many of the fancy learning algorithms you find in PyTorch and in the literature. And it's surprising to me how infrequently people use rprop because it's just so intuitive and so simple, right? Questions? Yeah.
But if I have the case, if you move like too large and the other side also, you calculate the derivative is also the opposite, like up to the left direction, and you will just ignore the like a minimal point in the middle, right? If the
So you're asking about a situation where I have maybe something like this, and I've gone all the way here.
yes.
That can happen, but it's very unlikely, right? Yes.
How do you not get stuck at a local minimum?
You still get stuck at local minimum. But the one thing is the step sizes keep increasing, so the likelihood of getting stuck at a local minimum are just smaller because eventually your step sizes are large, and when they begin shrinking, because you're going back and forth, you're probably at a big global minimum. Questions? Yeah.
So how do we know in what situations it'd be like effective to use this?
Optimization rules are, there are many different optimization algorithms, so I can't give you any rule of thumb for this. I wish I could. You just try. Except that this is really simple. If I were to be coding it, coding the other optimization algorithms is really painful. This is trivial, right? But the thing about this is that because you keep going forward and taking larger steps, and eventually, the moment you begin shrinking your steps when you overshot. So this is very likely to eventually end up in a very broad minimum. And broad minima tend to also be deep minimum. And so it's very likely to actually end up at a good local minimum, if not the global minimum. Yes, Miguel?
Right, just like you said, like the broad, the minimums tend to be like broad as well, right? The broader they are, the deeper. I don't know, but so it seems like the worst case is to get stuck in a saddle point than a local minimum.
So if you get at a saddle point, you could end up in the wrong place in one direction, but because you're moving in the other direction, you're going to get out of it.
Yeah.
Each component is changing, so the net is going to be away from a saddle point. Right? This works nicely with saddle points. Yes, David.
What's the advantage of returning to your previous location rather than just stepping?
You could do that. There are many different heuristics you could apply, right? So you can say I've overshot, and then I'm going to turn around and take a smaller step nonetheless. And all of this does happen. There are different variants of this basic rule, and all of them are strictly equivalent in terms of performance. So here is the pseudocode for it. I won't go over it. Typically, you have a cap the steps so it doesn't get too large or too small. And it still needs the computation of derivatives because you need the sign of the derivative. And the derivative is computed using, how would you compute it? Backprop, right? So it's a remarkably simple first order algorithm that's frequently much more efficient than gradient descent and makes only minimal assumptions about the loss function, no assumption about convexity at all. There's another, yeah. Any questions so far, guys? Okay, time's up. Someone on Zoom, can you tell me which of these statements is true? Zoom? Is there anybody on Zoom?
The first one.
The first one.
First one, thank you. I think we're going to have to begin issuing numbers from the next class. Folks on Zoom are not maybe paying attention. So one of the things we do to make sure that you guys are engaged is to give each of you a number or a nickname, and I'll call out the nickname, and you have to answer. And if you don't answer when I call out your nickname, you're marked absent for the class. So R prop will revert to the earlier estimate and take a smaller step, or the other heuristics you can employ. Another variant is quick prop, which uses Newton updates, except that computing second derivatives is really hard. So it computes an estimate for the second derivative for each component. This was invented by our own Scott Fahlman, and it's still one of the fastest training algorithms for many, many machine learning problems, in particular for neural networks. And I'd recommend that you actually try this. It's all on the slides. And so this gradient descent can miss obvious answers. This may be a good thing. Vanilla gradient descent may be too slow or unstable due to the differences between dimensions. Second order methods, which look at the second derivative, can normalize the variation across components. It's on the slides. This quick prop is one of these, but they're very complex. And adaptive or decaying learning rates can improve convergence, like in the case of R prop. But in every case, you really want to decouple the dimensions in order to ensure that you get your answer faster. Now, but then there's another approach to this. There are extensions to the basic gradient descent algorithm, which also sort of follow the principle of decoupling the directions. And all of them follow this very simple principle. Now, let's say I have a bunch of slides, but we're going to revisit this topic in the next class. So instead of going over the slides, let's say I have a objective function of this kind, and say I start off at this point, and then I find myself doing this. If I just use simple gradient descent, I find myself doing this. I find myself what have I learned from this?
2 times.
Yes.
So you converged in your y direction.
I converged in my y direction and in the x direction.
You're oscillating back and forth.
I'm oscillating back and forth. Now, so suppose I were allowed you to decouple the learning rates in the 2 directions. What would you do?
I would make the learning rate in the x direction smaller.
You would make the learning rate in the x direction smaller, but you'd keep the learning rate in the y direction, right? How do you know that the learning rate is bad for the x direction?
Oscillations.
Can you say that loud?
Oscillation.
I can just look at the solution. I find that the solutions in the y direction are just going there straight in one direction. In the x direction, they're swinging back and forth a whole lot, right? So based on this principle, can you guys come up with ways of changing the learning rate for each component? Just this simple intuition.
The sign is changing, so the change the correct function in between.
If the sign keeps changing for a component, maybe you want to reduce the learning rate, right? But is the sign sufficient? So is this going to be the same thing as this? No, you also have to look at the magnitude, right? Simple logic. You can just look at how it's behaving with respect to each of the components. And if in some components you're getting a monotonic convergence or convergence, then whatever step size you've got is good. If it's oscillating back and forth, maybe you're overshooting, you have to decrease your step size. Very simple logic. And this, once you actually think of it this way, I don't even have to explain what we do next. You guys can probably go off and come up with your own optimization rules, right? A lot of what's out there in the literature on optimizers and learning rate schedulers and such like are based on the simple principle. But just to give you a quick heads up, the 2 simplest principles that we're going to look at, we're going to keep track of oscillations. You want to emphasize steps in directions which converge smoothly and shrink steps in directions that bounce around. And one way to do this is to maintain a running estimate of the steps that you have taken. So if I take a running estimate, running estimate of the gradients. So the gradients have multiple components, right? We know it's possible for backprop computes the gradient for us. So we just have, that's what we have to take advantage of. Eventually, what backprop gives us is gradients. And so I can just keep a running estimate of gradients. Now, if my solution is bouncing around in one direction, then those components of the derivatives are going to keep changing direction. If it's going smoothly in the other direction, those components are going to keep the same direction. So what if I use a running average, not just the current gradient, but if I maintain a running average of all of the gradients, then the directions in which I'm always progressing smoothly are going to get emphasized, and the directions in which I'm going to, where the sign of the gradient keeps changing, sign of the derivative keeps changing, are going to get de-emphasized. And so the momentum method does something very simple. It actually maintains a running average of all of the steps, and it always updates using the running average. And this naturally accounts for, it naturally gives you a varying learning rate in each direction. And the extension to it is Nestrov's method, which does the same thing in a slightly different way. I'm just glossing over it because we will go over it in the next class. Because these momentum methods tend to be much more important when you're performing stochastic gradient descent. And so once again, the basic idea is the same, that you sort of maintaining a running average of the gradients and then update using the running average of gradients. So I'll stop right here. Nestrov's, the gradient descent and Nestrov's accelerated gradient descent are on the slides. Please look them up because they may end up in your quiz. But we will revisit them, and looking them up for the purpose of the quiz is a good thing because that means you're prepared for my next class. Any questions? Thank you very much. Yeah?